Hey there, AP Calculus students. This is Mr. Bean, and today's lesson is going to be on optimization. Calculus has its tendrils in lots of different fields: economics, business, medicine, all sorts of different sciences. And the reason why is a lot to do with this optimization, where we're going to try to find the most or the least of something. And so this is a great lesson to get really good at, because for those of you who have to take a calculus class in your future, a lot of it may be focused on this stuff. So I've got some examples here, and then I'll talk about the strategies at the very end of the lesson. So let's go ahead and just jump into this. Finding two numbers whose sum is 30. So let's just say I've got two different variables, x and y, two numbers that I don't know what they are, but if I add them up, I know I'm going to get 30. And then I also know that their product, is going to be x times y. And I'll just say that that equals some capital P. P is going to stand for product. Now, when we look here, it's saying that this is, what do we want to make as large as possible? The large as possible is going to be this. So that means the large part means, if I were to come down here and kind of think about, I would have some type of maximum value. So when do we have a maximum value of the product? When its derivative is equal to 0, because I'd have a slope of 0, and the second derivative would be negative. So if the first derivative equals 0 and the second derivative is down, to make it concave down, then I've got a maximum. That's what I'm looking for on this. So how do I do that? I have to take the derivative of p to find p prime. But we don't want to do that yet, because I have too many variables, x and y. I just want one variable. So the way we do that is we take our other equation, and let's say that y equals 30 minus x, and I can use substitution now. So I'm going to substitute that into that y. And that gives me what? X times 30 minus x equals p. Let's multiply that out. 30x minus x squared equals p. All right, now let's go ahead and take the derivative of that. So that's 30 minus 2x equals p prime. So I want to figure out, when does the derivative equal 0? So let's say that this thing equals 0. So I would, if this whole thing is a 0 right there, I'd subtract 30, divide by -2, I get x equals 15. So x equals 15, and then let's double check. Is the second derivative, what's the second derivative? Here's the first derivative. So the second derivative is going to equal -2. So it's concave down. The first derivative equals 0, so this is a maximum. So if x equals 0, or x equals 15, y is also 15. There are my two numbers right there. So that first example gave us the basics of how this works. We're going to set up an equation that we want to take the derivative in order to optimize, to find either the largest or smallest of something. And then it can only have one variable. So sometimes you'll need another equation that you can manipulate to plug in to give yourself only one variable. But then you just take the derivative, double check that it's a max or min, and then you're good to go. All right, number 2, what point on the graph y equals the square root of x is closest to 5, 0. So I gave you the graph so you can kind of visualize this. So we're looking for a point along the square root of x curve that is closest to 5, 0. So maybe, is it this point? Is it this point? Is it, oh, obviously it's not that, it's getting farther away. So that's what we're looking for. Well, how do you figure out the distance between two things? You need the distance formula. So this will come in handy for us in today's lesson, in the practice. The distance formula is an adaptation of the Pythagorean theorem. So it's where I have some x value minus another x value squared. So it's the difference between two x values plus the difference between two y values. So I'll say this one y value minus another y value, square it, and then it's the square root of all that. So it's again, it's a variation of the Pythagorean theorem to get the distance. All right, so what are we going to do? I'm going to make a list of my two coordinate points. So I have 5, 0, that's easy. And then my other coordinate point is going to be x, comma, square root of x. So let's see if that makes sense. The other x value is just whatever you plug in, and then the y value is the entire function, that whole thing. So this is the distance that I'm going to be, or the two coordinate points I'm using. So let's plug all that in and see what we get. Okay, so there's my distance formula, and I'm going to have to remember, I'm going to need to figure out when the derivative of that, because this is what I'm trying to optimize, I'm trying to find the smallest, the closest, when that distance is the smallest. So when does the derivative equal 0? And then the second derivative should be greater than 0 in order to have a minimum. That's the two things I'm looking for this problem. Let's see, before I take the derivative, why don't I clean this up just a little bit on this particular problem? I think this will help. This becomes x squared minus 10x plus 25. Over here I have plus an x because the square root of x squared. And then this just becomes minus 9x in the middle. So it's this thing with a minus 9x. So the derivative now, the derivative of the distance is going to be, I have 1 over 2 square root of x squared minus 9x plus 25, and then times the derivative of the inside. So now I'm going to have times the derivative of 2x minus 9, the derivative of the inside here. Okay, so that's the derivative. When does this thing equal 0? It's going to equal 0 only when the numerator is equal to 0. So here's the numerator. So we solve that, we get x equals 9 halves. Okay, so if x equals 9 halves, is the second derivative greater than 0? Well, taking the second derivative, this is going to be a real pain. So maybe instead of doing this, maybe what I do is I think, do you remember those charts we did that Mr. Bruss showed us how to do when doing some values, doing some test values for first derivative and second derivative test? Let's try the 0.9 halves, because I know if I plug in a 9 half that the first derivative is going to be 0. So what if x is less than 9 halves? And what if x is greater than 9 halves? I'm doing this kind of sloppy, but we're just trying to check real quick. So let's plug in a number that's less than 9 halves, like 0. So 0, 0. I'm just looking to see if it's positive or negative. If I plug in a 0, I'm going to get a negative number. See, 0 here is negative 9, and then this thing's going to be positive. If I plug in a number that's bigger than 9 halves, so like 100, well, if I plug in 100, this whole thing's going to be positive. So if the derivative is decreasing, is 0, and then is increasing, then this is a minimum. So using the first derivative test, I didn't have to use the second derivative test on that one, I can verify that at x equals 9 half, that is the closest coordinate point. So the point is 9 half, comma, and then the square root of 9 half is 3 over square root of 2. And yes, you could rationalize that thing if you wanted. But that is our answer. Okay, Mr. Kelly's making a box to store all his magic cards, and we're going to make the box out of a 14 by 30 piece of cardboard. So let's, over here off to the left, maybe in the margin of your notes, draw yourself a little piece of cardboard. And it is a 30 inches by 14 inches. Okay, so it's 30 by 14. Again, do this off on the left side so you give yourself some more room. And what we're trying to do is cut out some squares. So I'm going to cut out some squares here and here. And all I know is that these squares, that's not really a square, but you get the idea, close enough. These squares are supposed to be equal 4 corners, equal size. So I don't know how big they are, so I'm going to call this a distance of x, a distance of x. Same here, this is x, and so forth. So every little one, this is an x by x square from each corner that we're going to pull out. What size should the squares be in order to create a box with the largest volume? So when it says largest volume, that means we are going to figure out a formula for volume and find the optimal largest possibility. So I'm going to write off here on the side just to remind myself I'm looking for when does volume equal 0, and when does the second derivative, if I want a largest volume, that means the second derivative it's got to be concave down, so the second derivative should be negative. Or I might have to use the first derivative test with a little chart, depending on the problem. Let's just see how we go. So I know that volume is equal to length times width times height. So we need to figure out length, width, and height of the box if we were to fold these corners up. So this is where it gets a little tricky, kind of visual representation here. Ooh, this is difficult. I will tell you here that, so the volume is going to equal, the length is right here of this box, just this piece, from this end to this end. Well, if the whole thing is 30 on the whole side, if this whole thing is 30 from here to here, then I'm going to take out this piece and take out this piece. So I'm taking out the two x's. So my length is 30 minus the two x's. And then the width, it's the same idea. The whole thing across is 14, and I'm taking out those two x's. So the width of this box is 14 minus 2x. And then the height of the box, if you can visualize folding this thing up, how tall is it going to be? It's going to be a height of x. For the next step, I'm going to save us some time. I went ahead and multiplied this whole thing out so I can see. Honestly, I needed a calculator because those are big numbers. And that gives me 420. So I FOILed this, multiplied it out, and then distributed the x. 420x minus 88x squared plus 4x cubed. All right, so again, we're looking for when is the derivative of volume. So this is the volume of the box. And depending on how big we make x, the volume will change. So the derivative is 420 minus 176x plus 12x squared. So when does this thing equal 0? Okay, so there's a couple options we have here. If you're using a calculator, it's not that bad. We could just use the quadratic formula. A lot of times kids think, oh, I have to factor it. No, you don't have to factor. I would just use a quadratic formula, but since we're saying that when does this equal 0, there is a number that we could divide out of each one of these. If you divide each of them by 4, so I'm going to bring this to the front, divide this by 4, and I get 3x squared minus, this one becomes a 44x, and why do I know this? Because I already did it on my calculator to double check. Divide this by 4, and I get a plus 105, so I just rearranged it to be standard form.
Okay, so let's stop right now and recognize there's different ways we could do this. Yes, quadratic formula, negative b plus or minus square root of b squared minus 4ac all over 2a. Or we could try to factor this thing. But also, if the algebra is kind of difficult in this lesson, you can go ahead and use a calculator, and that is just when does this thing equal 0? You've got to be good with your calculator stuff, but once I've done that, so I've plugged this into y equals, I changed my window. I played around with my window until I could see it, and this is what my window was in case you were trying to do it on your own calculator. And then I graph it, and here is that parabola. Now, I actually could have done it, look here, I could have done it right here, this 420 minus 176x plus 12x squared. I could have plugged that into the calculator as well, gotten the exact same answers. The graph would have looked different, but it's still going to cross at these 2 points. So let's figure out second calc. Where are those zeros? So option number 2, and hit enter. And let's see here, my left bound. Now I could go ahead and move my boundary left, or watch this trick. I know that 1, I'm going to type in the number 1, x equals 1, and enter. And it'll jump right there, and that's my left boundary. And then 1, 2, 3, 4, 5. I know if I type 5 as an x value, then 5, enter, then I know that's going to give me my right boundary, and now I can go ahead and just hit enter, and it'll find the 0 that's in between these boundaries. Enter, and there it is, x equals 0. So let me come back over here and write down that x equals 3. X equals 3 is one of my zeros. Now let's go back to my graph. Do the same thing for this other one here. I'm going to calculate the 0. And again, let's just say somewhere in the middle here, x equals 5. This will be my left boundary. And my right boundary, I know the right of my screen was 15 because I chose my window as that. So let's say 14 is my right boundary. Hit enter. Boom. Or I could have just scrolled all the way over to the right here and hit enter. And now I want that one, so I'm going to guess in between these two boundaries. And what is it? 11.667. So over here, so x equals 11.667. Okay, so now one of these is the answer and one of them is not. And you have to think a little bit about which one makes sense for the problem. If you had 11.667 was the size of this x that you're cutting out for the square, well, the side's only 14 long. So you can't have an 11-inch cutout here and an 11-inch cutout there when that's a total of 22, 23. I mean, it can't even fit there. So that one just, it makes no sense to use this answer. And so our answer is x equals 3. And so then what was the question? What did it ask? What size should the squares be? The squares would be 3 by 3 inches. There we go. Boom, there's our answer. Okay, let's go on to the next one. Example number 4, we got a couple towers going on. This problem is a doozy. Stick with me. You're going to have one like this on practice, and I think at least one of the versions of the mastery check will have this, maybe even the test. Oh, man. Okay, so let's have a wire, or a tower, I should say. Let's do one tower here, and then another tower here. We'll make this one a little bit taller. And what am I doing with these? I'm saying that one is 12 feet high, so let's call this 12 feet high. And this one is going to be 28 feet high. And there's a stake in the ground that's between the two towers. So let's put the stake, I don't know, maybe somewhere right here. It doesn't say that it's right in the middle. And the top of each tower has a wire that is tied to it. So I'm going to have a wire from here to here. And then I'm going to have another wire. I'm going to change my colors from here to here. So, what does it ask us to do? Where should the stake be placed to use the least amount of wire? Okay, so I want this green and red lines to be the smallest possible thing. So I'm going to call this one my W1, my first wire, and this one will be my W2 for my second wire. So I'm going to have a formula over here that says that W, the wire, is going to be my W1 plus my W2. And this is the thing I want to optimize. So I want to optimize this equation by taking its derivative. So I'm going to go W prime, and then whatever W prime is, I set it equal to 0 and solve. First, I need to know what is W1 and what is W2. Okay, that's not too bad because I can use Pythagorean theorem. So watch this. Let's say this distance from here to here I don't know. Let's call it x. And then this distance from here to here I also don't know, and I could call it a different variable, y, except that I know that they are 30 feet apart. I know the two towers are 30 feet, so if the whole thing's 30, that means this distance right here is 30 minus x. Okay, so now Pythagorean theorem tells me that my W1 is going to equal the square root of x squared plus 12 squared, which is 144. All right, there's my W1 wire. And what else do I do here? I'm going to say my W2, I'll use my red. My second wire is going to equal the square root of, let's see here, this squared and this squared. So 28 squared, I need a calculator. 784, and then plus 30 minus x squared. So 30 minus x quantity squared, I should say, because it's the whole thing that's being squared. Okay, so now what do? I take my entire wire, length of wire, is these two things added together. So my W equals the square root of x squared plus 144 plus the square root of, I'm going to multiply this thing out, 30 minus x squared. Let's do that up here. 900 minus 60x plus x squared. So the reason I did that is because now I can kind of simplify what's underneath the radical by multiplying this thing out, or adding this together. I get 1684 minus 60x plus x squared. Okay, there's my entire wire, formula for the entire wire. Now we take its derivative. So the derivative equals 1 over 2 square root of x squared plus 144. Oh boy. Now I have to take the derivative of the inside, so I'm going to times that by 2x. and plus, now I take the derivative of this whole thing. So the derivative is 1 over the square root of 1684 minus 60x plus x squared, hopefully you can read this, I'm trying to write small, times the derivative of the inside. So I now times the derivative of the inside here, which is just going to be a negative 60 plus 2x. Oh, I forgot a 2 in front. I forgot a little 2 right there. 1 over 2. Okay, I need to make more room here. So now, if we remember, since we're just optimizing the wire, we had to find this wire's length and set it the derivative equal to 0. So now we take this whole thing here and we set it equal to 0. And yes, you could just use a calculator to do that. We don't need to go. I mean, I could clean this up a little bit because you can see here that 2 and that 2 is going to cancel. So, and then what else here? I could divide this whole thing by 2 and cancel it with this 2. So that would make this, I'm going to rewrite this as x minus 30. If you can see that here, because switch them around, divide it by 2. Okay, so that's where that goes from. So what I can now plug into a calculator is I have x over the square root of x squared plus 144. And then what? I've got plus x minus 30 over, and then on bottom, the 2 is gone, and I just have the 1684 minus 60x plus x, oops, there we go, x squared. That's all underneath this radical. That needs to equal 0. So I can go ahead and type this whole thing into my calculator, set it equal to 0, and just find the x-intercepts. So let me do that and have that pop up here on the screen. Okay, so you can see here I have this all plugged in. You have to be careful with the numerator there, this x minus 30. Now, my window, this took me a little bit of playing around with, but I figured my min and max for my x values, it can't be more than 30. I mean, look here. If my x is just this distance of the wire, the largest it could be would be 30 if I tied it all the way over here, which would be weird. So I know it can't be that. In fact, I probably could have even said 15 because it's going to be, well, no, because it might have been more than halfway, so I didn't want to do that. So 30 was fine. And then my y min and max, I had it too large at first, so I just kept making it smaller and smaller until I got this nice, pretty graph, and I can see that is the answer, wherever it crosses the x-axis. So let's go ahead and figure that out. Second, calculate. Where do I want a 0? So option number 2. And I'm going to just type in a number. How about 1? X equals 1, I know will be way over here. Boom. And then how about like 20? I know I'm safe if I say x equals 20 because that'll be way over here. And then it's going to search in between those if I hit enter. And what is it? The answer is, hello? There it is, 9. X equals 9. So I come right here and write x equals 9. There we go. So, in fact, do I box that answer? I think I'm boxing that answer. Well, I guess what I should say is the x should be 9. So my real answer would be that I'm 9 feet away from who? Which is the 12 feet tower? 1 is 12 feet tower. 1 feet, or 9 feet from the short tower, something like that, just to be able to distinguish where the thing is. Okay, so you can see here we saved ourselves all the headache of all the algebra there and just used the calculator. So let's take a look at a summary of the strategies when trying to optimize.
Here we go. Here's the summary of the lesson. So the strategies that you want to use is, if you can draw a picture, go ahead and draw the picture because it's really confusing to try and figure out what's going on with all these things. And then identify what's the known and unknown quantities. Things you know, put the numbers down. If you don't know what it is, of course, you're going to use variables. Then we write an equation that is going to be optimized. Remember, if it was volume and we're looking for the largest volume, that's the one we want to figure out for if that's what we want to optimize, then we say that the v prime would equal 0. That helps us keep track of what we're looking for. Make sure your equation is with only one single variable, so you don't have multiple variables that you're taking the derivative of. And then determine the desired max or min value using calculus techniques as we've talked about in previous lessons. And then also, I didn't really do an example of this, but sometimes you got to make sure, do you have domain endpoints for your equation, just to verify if your endpoints are part of the max or min. And you'll see that depending on, once in a while we'll have a problem. There's not going to happen very often, but once in a while we'll have a problem where there is a restriction on the domain where x is going to be in between, like 1 and 20. And so you'd also check the endpoints for that. Okay, that's it for this. I hope those examples will at least get you started on these practice problems. You can also check the corrective assignment if you feel like you need more problems. I've created 2 corrective assignments for you to go through if you need it. All right, rock that mastery check, and I'll see you back in Unit 7.